April 2020 semester ICT 6900 স্পেশাল টপিকস ইন ICT অ্যাডভান্স মেশিন লার্নিং কোর্সের লেকচার 7 এ সবাইকে আমন্ত্রণ জানাচ্ছি। Today's topic is support vector machine and we'll cover this new algorithm, and this is under supervised learning algorithm. So SVM is the last algorithm on supervised learning algorithm that we plan to discuss. The performance of a learning algorithm is determined by the amount of features that can be handled and the way the regularization parameter is handled. SVM is very powerful and popular algorithm, and it is widely used both in the industry and by the academia. When compared with logistic regression and neural network, sometimes the SVM gives more cleaner and sometimes more powerful in learning complex nonlinear problems. So what is SVM? So before we introduce SVM, let us make a review on the logistic regression. And if you remember, logistic regression is represented by this hypothesis, which is called sigmoid function. In the x-axis, we put z, where z is equal to theta transpose of x, and y-axis is the hypothesis. And theta is the parameter, and x is the input features. So h is the predicted output, and we compare this h with the y. Y means the given output, and then we find out the error, and from this error we calculate back the theta and so on until it converts. And we want that h theta x should be equal to 1 when theta tx is very large, that means very greater than 0, when y is equal to 1. That means when output is 1, our objective will be to make theta in such a way that theta tx is very larger than 0. So this is the value where we can see that theta t is much bigger than 0, and at that level the output is close to 1. And when y is equal to 0, the case is y equal to 0, we want that h theta x is equal to 0, because at high value of theta tx, in the negative axis, high value of theta tx, the hx becomes 0. So this is what we discussed so far in our course, in our lecture of logistic regression. And if we see the cost function, cost of example, on a single example, then we can write this one. We have discussed about this equation where hx can be replaced by 1 over e to the power minus theta tx, and in this case also hx is replaced by this equation. And if you remember, this equation, this part of the equation is responsible for y equal to 1, and this part is responsible for y equal to 0. We combine both in a single equation by putting in this manner. So if you remember the plot of this part, the curve is like this one, where minus log of 1 over 1 plus e to the power z varies logarithmically. And if we approximate this curve by these two lines, where one line is a straight inclined line, and other part is 0, then that will be a simplification of the original equation. The log equation, the previous one is a log equation, and now the cost function for y equal to 1, this part will be the logarithm equation. Similarly, if we look into the other part of the equation, the equation was like this. If you remember, the logarithm equation varies like this. And if we approximate this equation like the previous one, the equation will be like this one, inclined line and also a constant 0 line. So instead of having logarithm equation, we can put this equation in the cost function. That will simplify our result. So what effect it will have in the if this approximation is made, what effect it will have in the cost? Because the variation will be simplified, and if we use the simplified equation, the all the concept will be simple. Let us now discuss about cost function for support vector machine, and this is derived from the logistic regression concept. And we have seen in the previous slide the expression for cost function in logistic regression is given by this equation, where we have assumed that this particular part, that means the first part of the cost function, is represented by approximate curve. Let us call this is cost 1 theta t xi. Similarly, the other part contains the another logarithmic part, and we have approximated that logarithmic part. And let us assume that this part is called cost 0 theta t xi. So these are the two approximate functions. We'll replace this logarithmic function by approximate linear function. So our equation for vector machine will be like this one. So just replacing the linear function with the logarithmic function, or replacing the logarithmic function with the linear function. So this is our cost 1 theta t xi, and this is our cost 0 theta t xi. And some other assumption is made. For example, the m term in this equation is withdrawn, because this is a optimization equation. So if a constant multiplier you give in the constant equation, it doesn't matter whether you put the constant to any value. And in that manner, this part let us call A, and lambda you take separately. Lambda is the regularization parameter, and the rest of the term except the lambda, that are half of this summation, is B. So our cost function we can write for linear regression, cost equal to A plus lambda into B. When I say linear regression, the m term will be there. So the term with m, let us say A, the term with m except the lambda, we call it B, and lambda will be there as a constant. So the cost function will be 1 plus lambda into B. But for support vector machine, let us say m equal to 1 in this particular equation. M is not equal to 1 in all cases, but for the cost function, let us say m equal to 1, or we just remove this constant factor. Then the cost linear regression for support vector machine, the cost is given by the similar equation, but we call it CA plus B. The difference between the two equations is the lambda parameter or constant parameter is with B, and for support vector machine there is another constant parameter which is with C. So we can say that C is equivalent to 1 over lambda. That means when lambda is very high, C should be equal to close to very small value or close to 0. Similarly, if lambda, in cases where lambda we assume very small value, then C has to be very high value. So these two equations are very similar. Only thing is that you have approximated a cost function where we remove some constant value, and also we introduce a constant with C rather than with B. So our final equation for support vector machine will be minimization of this equation, where the first term will be with C and the last term is half of j equal to 1 to n theta j square. You remember j should be from 1, not j is from 0. And in the internal logarithmic part, we'll just name cost 1 and cost 0. These are the linear equation, linear approximate equation. And if I elaborate a bit more the cost function, if you see the curve was like this one. You see, this is your cost 1 z, and this is your cost 0 z. And we have also already stated this equation that if the y equal to 1, that means if the given value is 1, we want that theta tx should be 1, not greater than 0. In case of logistic regression, the condition was theta tx greater than or equal to 0. Now we are making a bit more safety factor. Instead of 0, let us say theta tx should be greater than 1. So it will make, in the 0 to 1, it also very small, but it will be exactly 0 if we can bring theta tx over this range. So optimization objective will be to make theta t in such a manner that theta t is greater than or equal to 1, so that cost becomes 0. Similarly, in case of output, where output is equal to 0, we want theta tx should be less than minus 1. If you see the curve, if the theta tx is less than minus 1, the cost function will be 0. So if you want to have a more safety factor, you should bring theta tx less than minus 1, not less than only 0. So this 0 term that we use in the logistic regression, the 0 value, should be replaced by these two values. In the case of positive example, we will bring theta t in such a way that theta txi should be greater than 1. In case of negative examples, that means y equal to 0 cases, we will put theta tx, we will try to minimize theta 2x when this value becomes less than minus 1. That means in this region. The negative example in this region and positive in this region. Always you can see the cost function, we will try to make the cost function equal to 0. So this is the range we call z greater than equal to 1, and this is the range we call z less than or equal to minus 1. So this is our discussion that we made. So we have to make it very careful about writing the equation that theta tx greater than 1, not greater than 0, and then cost function will be 0. And if theta tx is less than minus 1, that means in this region the cost will be also 0. So in both cases, if you want to make the cost minimum, that means if you want to make cost 0, our objective will be to make this theta tx in this region or in this region. So in both cases, if we can bring theta t in these regions, that means the cos theta tx in this region, z value, then we can say the first part will be equal to 0 for minimum cases. So the equation will be like this: c multiplied by 0 plus half of j equal to 1 to n and theta j square. So the objective function for support vector machine will be very simple like this one, because our objective is always to make that 0. So if you can make this value, this particular value minimum, the summation of this value multiplied by half, if it is minimum, then the cost function will be minimum. So what is the effect of SVM on decision boundary? Let us take a case of linearly separable case. This is a case where we can easily see the two sets of data, the positive and negative data, they are linearly separable. This can be written by this equation, as we have seen, the minimum cost function, minimization of the cost function. And let us say this is the decision boundary. This line actually separates the two lines. But both the cases, red boundary or green boundary, both the boundary actually marginally separates these two lines. But support vector machine makes the decision boundary in this manner, where you can see this is more robust linear separation. because this boundary makes the two sets of data away from one another. This boundary, we can say, the most efficient one. And this is most efficient because this creates your margin, because this particular data is separated from the decision boundary with a margin, and this set of data is separated by this line with another margin. So these are called the margins. So sometimes support vector machine is called large margin algorithm. So we'll talk about this later on. So if I see the effect of decision boundary on the presence of in the presence of outliers. So for example, in this case, you determine a decision boundary, maybe this one, but if there is a outlier, say this is an exceptional data, which is not in this group rather than another one, we could actually separate the two sets of data still now by this line. But that will not be very wise, because a single data should not make the decision change. So this line to that line, why that will be shifted, and you will get this shifting in case of logistic regression, and this will happen in the support vector machine also if C is very large. We'll talk about that later on. If C is very large, a single outlier will make this particular shift of the perfect decision boundary. We call this is perfect because this boundary made these two sets of data with a large margin. 1 over lambda is equivalent to C. When you see C is very large, that means we are corresponding to lambda is very low. And we have seen in the previous cases, in the case of logistic regression, lambda should be actually high value. So in that manner, C, assuming C is a very large, is not natural one. And in case of the other outlier, like in this group or in this group, if there are more outlier, we call it outlier because these are not normal data in the group of the positive and negative example. So in case of this outlier, the decision boundary could change further. But in case of support vector machine, this boundary will always remain close to this one, because the main objective of this support vector machine is to make a large margin on the linearly separable cases or in the nonlinear separable cases. The main concept is, in case of support vector machine, is to create a classifier or create a decision boundary so that it will have a large margin. And this will happen if somebody choose C not too large. C has to be small, and in that case the decision boundary will be robust, and with the term robust it means a boundary which will have large margin. So let us now discuss about the support vector machine, the concept of support vector machine, how this particular algorithm makes the decision boundary robust. And before we go into the detail of mathematics, let us clarify some basic concept. And the basic concept on vector inner product. If you have a vector called U, which has two components, U1 and U2. In the x-axis U1 and the y-axis U2. The vector may look like this one. The components are shown and the vector is shown by U. Similarly, if your vector have the new vector is V, then V could be in the xy plane, looks like this one, with having with V1 and V2. So let us try to find out what is U transpose V. What is the meaning of U transpose V? The U modulus is the length of vector u. That means the length of the vector. That means the length starting from the origin up to the tip of the vector. The length is determined by u modulus, and in mathematically we call it from Pythagoras equation u1 square plus u2 square square. So let us now define another scalar term, which is length of projection of v onto u. So if you take a projection from v tip onto u in this line, so this is your p. If you take a vertical line from v tip onto u, then the length will be called p. And mathematically it can be shown that u transpose v, that is our point of discussion, is nothing but this p multiplied by magnitude of u. So this magnitude multiplied by this magnitude. This magnitude is the magnitude of vector u, and this magnitude is a length of line which is projected from the vector v up to the a. And mathematically, this is equal to u1 v1 plus u2 v2. If you transpose this one and multiply with v, you will end up with this equation. By the way, this equation is same as v transpose u. If you take projection of u onto v, and if you call that is p multiplied by v magnitude, will be same as this is obtained from projection of v onto u, this p multiplied by u. You should remember that p is a signed number. It can be positive, it can be negative. For example, in this figure, u and v are 90 degree, more than 90 degree apart. Then apart, the angle of separation is more than 90. If you take projection of v onto u, you have to back project it and you will get a value p. If the p direction is in the opposite direction of u, then we call p is a negative. This negative is in the sense that with respect to the u, so it can be negative. So this vector multiplication or vector inner product u to v can be either positive or negative depending on the angle between u and v. If the angle between u and v is 0 to 90 degree, then the result will be a positive result, and if it is angle is more than 90 degree, the result could be a negative one. It's not 0, but it can be negative value. Let us now see how the concept of vector inner product is applied in explaining support vector machine. So the objective function is this minimization equation where we express like minimum over theta, half of summation of theta. So this objective function is our target to find out the parameter theta. So subject to this condition, of course, theta t xi should be greater than equal to 1 if the output is 1, and this product has to be less than or equal to minus 1 if the output is given as 0. So let us make some simplification where theta 0 is assumed to be 0. That means the intercept term is neglected, and number of features and number of parameters is n equal to 2, and this is expressed by half of theta 1 square plus theta 2 square, which again can be written as half of square root of theta 1 square plus theta 2 square of whole square, and this is nothing but half of the magnitude of theta square. So now let us try to find out what is the value of theta transpose xi, the value in this condition, theta transpose xi, what this product is meant for. We have discussed about UTV, so this is analogous to the theta t xi is analogous to u2v. So the same concept we can apply here. So let us say this is our diagram for vector of theta and xi. Theta is the parameter and xi is the input features. So if we take the projection of xi over theta, then we can call this brown line as a pi. For ith example, what is the value of p? So this xi consists of x1i and x2i, and theta is consisting of theta 1 and theta 2. So the multiplication of this pi and theta will give you the answer that we are looking for is qt of xi. So you can write qt of xi is equal to p multiplied by magnitude of theta. So this is the quantities, this is the p, and this is the theta. So this is our final result that we want to proceed on if we want to explain the support vector machine. Let us now explain how SVM decision boundary works. So this is our modified condition of objective function, modified in the sense that the subject to equations like xi, theta t xi can be written as projection I into theta, and that quantity has to be greater than equal to 1 if output is 1. For our cases where output is 0, the product quantity, that means pi projection of xi over theta pi multiplied by theta, magnitude of theta, should be less than equal to minus 1, where pi is the projection of xi onto vector theta, and we applied simplification theta 0 equal to 0. That means intercepts are equal to 0. So let us analyze over this set of data. First of all, let us say the decision boundary is this one, and it can be proved that the decision boundary, if this is the line, then the theta vector should be perpendicular to that line. Or in other words, if theta vector is determined, then you can find out the decision boundary by drawing a perpendicular line to the theta. So if this is the theta line, and if let us say this is x1, the first example, and then if I draw a projection of this point over theta, then this will be the red portion will be your p1. So p1, and this is greater than 0. And if p1 is greater than 0, then this objective, which p1 multiplied by theta I, has to be 1. And if that has to be 1 and p1 is very small, you can see from the figure the p1 is not very large value. So if our p1 is small, then theta has to be high. So theta has to be large value. But you can see the minimization problem says the summation of all theta square has to be minimum. Let us see another point, which is x2. x2 in the negative example side, and if I take projection from that point onto the theta axis, and then that will be your p2, and you can see this value is negative value because this is in the opposite direction of theta. So in this case also, if we analyze the p2 theta, so theta 2, p2 multiplied by theta, if that has to be minus 1, and p2 is very small, so theta has to be large as well. So in the both cases we can see in this example, if the decision boundary of that particular line, which is not very good line with respect to the robust one, the robust one is something where the decision boundary has a large margin. In this case you can see the decision boundary is closer to the point. It is dividing the two regions, but it is very closer to the point. And in both cases, since pi projection is small, then we can say the theta has to be large, which does not satisfy the minimum condition. We expect theta has to be smaller value, as small as possible. So let us take another case where decision boundary is this one and theta is this one. So if we take the projection of the xi, the same point, then we get p1. And you can see this is also greater than 0 because if that portion is small, so you can say that portion is larger than the other. In that case, if the condition pi theta, p1 theta, for example, this case has to be 1, so theta can be small. The previously theta has to be large, but in our case, theta can be small. Similarly, for the other point, the projection is the green portion. If we take the example, then this equation comes. That means P2 projection term multiplied by theta magnitude must be less than equal to -1. It is less than 0, so it will be negative. But since this value is high, the P2 and P1 are very high value. That's why theta can be made smaller. So theta can be smaller. So that is the advantage of this particular decision boundary, that if the decision boundary is that position, then you can have larger margin. So large margin classifier is the SVM. So one thing we have assumed that theta 0 has to be 0, but if theta 0 is not 0, then the decision boundary will not go through the origin. Rather, it will go to another point where there will be an intercept. So that is the difference. Otherwise, the concept is very similar. Previously, we talked about linear decision boundary. Now let us discuss nonlinear decision boundary. Let us see this example. The red crosses are positive examples and circles are negative example, or true and false. These are the true and those are the false. And if you want to make a nonlinear decision boundary, we discussed earlier that the hypothesis could be of this polynomial type, where you can see the features are x1, x2, x1 multiplied by x2, x1 square, x2 square, etc. These polynomial features are created. The original feature is x1 and x2, and you can compute these other polynomial features. If you put this extra term other than the linear term, then that hypothesis can make a nonlinear decision boundary. We discussed about this fact earlier in earlier lecture. So in this case, we will predict y equal to 1 if the hypothesis is greater than equal to 0, and if the hypothesis value is less than 0, then we predict y equal to 0. So this is our statement that we followed earlier. The prediction will be 1 if the right hand side is greater than 0, if the prediction will be 0 if the hypothesis is less than 0. And this is similar to, the hypothesis is similar to this one. Instead of writing x1, x2, x1 multiplied by x2, etc., we can write theta 0, theta 1, f1, theta 2, f2, etc., where f1 is x1, f2 is x2, f3 is x1 multiplied by x2, f4 is x1 square, etc. So instead of writing in terms of x, we can write in terms of f, where the equation is nothing but a linear equation, where the features may be non-linear, but the features are actually the calculated features. Original features x1 and x2. The collected data collection was made with x1 and x2. But is there any different or better choice of the features f1, f2, and f3? Instead of writing in this way, that means multiplying or taking power, whether there are better or different kind of choice of this f1, f2, f3, etc. So the concept is called kernel. We can define some vector where we call that vector as a landmark L1, L2, L3, and we express the given x in terms of L1, L2, L3. In other words, we'll compute L1 and L3 when x is given. X is the input features. So let us say this is one of the landmark or vectors. The another one is L2, maybe in that place, and let us say another landmark is L3. So kernel is nothing but transferring your given x into a other set of vectors following some equation. There are different kind of kernel, and we'll discuss just one, and we can apply other kernel in our practical life if you study those other equations to represent or to convert the given x into the landmarks. So given x, f1 is calculated, and f1 is nothing but similarity of x with L1. So the mathematical equation is like this one, e to the power minus absolute value of distance between x and L1. X is a given value and L1 is our new vector or landmark L1, and that distance squared divided by 2 into sigma square. Sigma is a constant. Similarly, f2 is another feature, and which is called similarity of x and L2. And by the term similarity, it means how close x is with L. In case of this, x with L1, and in this case, x with L2. So there will be another feature vector, which is f3. It's not feature vector, it's just feature. That means scalar quantity. So similarity of x and your L3. That means if, for example, if this is the x at that point, so how close that point to L1, how close that point to L2, and how close that point to L3 is given by f1, f2, f3. So instead of writing the equation that we have used in the previous slide, f1 equal to x1, f2 equal to x2, f3 equal to x1 multiplied by x2, etc., we will now define the features with this equation, and that will be advantageous in terms of support vector machine. So this kind of equations is called kernel, and this is a particular type of kernel which is called Gaussian kernel, and it is defined by this equation: k kernel, k of x and Li. I is in this case 1, 2, 3. So k stands for similarity of x and Li. So now let us discuss more about kernel and similarity. What is the meaning of similarity? Let us say f1 is given by this equation, which we have discussed in the earlier slide. So similarity of x and Li is e to the power minus x minus Li L1 magnitude square divided by 2 sigma square. And this is nothing but this equation, because there are n number of features. So every features you take the difference and then sum them together. First of all, square them and then sum them together. and this is equivalent to the vector difference, and then take the absolute value of the vector difference or the distance between the two vectors. So if we have the separate axes, for example x1, x2, and if L is a chosen landmark, then that will have L1 and L2. So you can have the differences between the each and every component. Then you take a square and sum. So for example, x is very close to L1 in the previous figure. If a certain given x is very close to a chosen landmark L1, then it will be exponential of 0 square divided by 2 sigma, because if they are very close, the differences will be 0. So f1 will be equal to 1 because e to the power 0 is 1. Similarly, if x is far from L1, so you can see the exponential minus a large number square divided by 2 sigma square, which is equal to 0. E to the power minus a large number is equal to 0. So these features actually measures the proximity of a given x with the landmark. So for L1, we will calculate this f1, f2, f3, and sorry, for L1 we will calculate f1, for L2 we will calculate f2, and similarly for L3 we will calculate f3. Why? There are 3 number of landmarks. Why not more? Why not less? We will discuss this later on. So let us discuss this equation. That means landmark, if there is one landmark, you will get f1 if the data point is also 1. That means if x is the only input vector, then we will have this set of f1, f1, f2, f3. So L2 will give you f2, L3 will give you f3. And these are actually replacement of x. Previously we used x1 and x2. Now we'll use f1, f2, f3 if you decide to choose 3 landmarks. If you want to choose more landmark, the f will be more. Similar to the polynomial equation. So let us see the plot of f1 with respect to x1 and x2. It's a 3-dimensional plot. For a certain value of x1, x2, what will be the value of f from this equation? That is shown in this particular 3-dimensional plot. Let us assume that sigma square is equal to 1 and x given x is also 3, 5, where landmark is also 3, 5. So if the landmark and the given x are same, then you can say these distance will be 0, so f1 will be 1. So this is the point, the red point, where we can see the value is 1. So in the bottom you can have x1 and x2, where x1 is in this case 3 and x2 in this case 5. But if you change other x1, x2, that means x value is changed, you can see the value is not 1. It will gradually decrease if you change in that path, and it will be 0, exactly 0, when x1, x2 in that position. In the black positions are the value of 0 for f1. So these are the plot of your f features vector, and the bottom one is actually the contour plot. The circles indicates a single f1. For other f1 is another circle. So similar to the previous diagram, the next one is also a plot and a contour, and this is for sigma square equal to 0.5. So now we can see the effect of sigma square on the f1. So if sigma score is reduced, you can see the plot becomes steep. That means the change in F1 will be sharp. From this point to this point, you can see it is changing sharp rather than this change. Similarly, if I plot sigma square equal to 3, plot for sigma square equal to 3, you can see the change is rather more slower actually. And this slow nature is because sigma square equal to 3. And the bottom one is again your plot or contour, not plot, contour of the equation. So this particular diagram shows how F1 changes with x1, x2 for a given landmark. So if it is close to the landmark x, then it is 1. If it is away, then it is 0. Let us talk about what do the landmarks signify. In our previous discussion, we have shown that if there is a x in this plane, that means a feature x which has two components x1 and x2, that means the x is changed to f1, f2, f3. The feature x can be converted into three features. One is f1, other is f2, other is f3, and those features are related to corresponding L1, L2, and L3. So these are the replacement of different inputs. Like previously, one was x1, other was x2, other was x1 multiplied by x2. So what these new features actually signifies. For example, there is a x over there, and if we optimize the theta, if we calculate the theta, we have not discussed about that. So we have not yet discussed about that how to find out this theta. But let us say that theta comes out to be these figures: minus 0.5, plus 1, plus 1, and 0. So the f1 will be 1 because f1 is close to L1. So since this is close, the value will be 1 as we have discussed earlier. F2 will be 0 because this L2 is far away from X. L3 will also be, F3 will also be 0 because L3 is far away from X. So if we compute this expression, the expression comes out to be 0.5, which is greater than 1. So with this calculation, we can say this is a prediction of y equal to 1. This is a prediction of y equal to 1. Similarly, the similar decision can be found out if we take the x as that point, because in that case f2 will be close to 1, but f1 and f3 will be close to 0. So theta 2 is 1, that's why ultimately the same result will appear. This point will predict y is also equal to 1. But if we consider another point which is far from L1, L2, and L3, all landmarks are away from X. And then if we proceed, we can predict y equal to 0. It can be shown by this calculation where f1, f2, f3 all are close to 0. So finally you can see the result is minus 0.5. The expression is minus 0.5, so which is less than 0. So you can predict that point as a y equal to 0. So this is how the results are calculated, and the influence of landmark is that it will help you to determine a certain point, either it is 1 or 0. So in this way, a boundary may be found out, nonlinear boundary may be found out of this shape. We have not shown all the points, but if you proceed, maybe the boundary will be like this. SVM support vector machine. There is a rules of choosing the landmark. So let us discuss how to choose the landmarks for SVM. So let us review the concept of landmark before we start the principle of choosing the landmark. So this is the three landmarks that we had chosen arbitrarily, and we calculate different features F1, F2, F3 depending on the number of landmarks. Given one single example, we determine different features, like previously x was the feature and there are two features x1 and x2, but now the vector x and the vectors L1, L2, L3 makes three new scalar quantity, which is F1, F2, F3, that constitute a vector called F. So Fj is determined by this formula, e to the power minus absolute value of x minus Lj. You have to remember that x is a vector, Lj is a vector. Lj means L1, L2, L3. L has two components, L11 and L12. Similarly, L2, L3, everyone has a same number of components. Remember that number of component in X should be equal to number of component in L. So these two vector, difference of these two vectors, if you take the magnitude and make it square, then divide by twice lambda square. And if you take exponential of minus of that value, that will be a scalar quantity. So Fj is a scalar quantity. Similarly, F1, F2, F3, where J is 1, 2, 3. 3 are the three quantities for F. So these three quantities constitute a vector that is called new feature vector. Previously, X was a one single feature which is also a vector, but now F is the converted vector with kernel. So we'll predict y equal to 1 if theta 0 plus theta 1 f1 plus theta 2 f2 plus theta 3 f3 is greater than or equal to 0. Now the question that we already mentioned, how to get or why to get L1, L2, L3. So these are the points, for example, where positive and negative example points are given. And first of all, you have to make all points with similar symbol, same symbol. You may point out the color. Color may be different to determine the 1 and 0 cases, but the treatment will be similar. That's why we change the shape to a similar shape. So the principle of choosing landmark is every given x will be treated as a landmark. That means landmark will be situated at the given point. For example, x1 was the given point. We'll choose x1 as a L1. So L1 is a landmark. Similarly, if x2 was that point, L2 will be that point. Same point we'll choose as L2. So if there is m number of examples, so we will have m number of landmarks. So L1, L2, L3 up to Lm. So using this landmark, we have to calculate for each and every example the features. For example, if you have a landmark of L1 to Lm, and if a single example of x1, then x1 with respect to L1, x1 with respect to L2, x1 with respect to L3, so on, x1 with respect to Lm. So x1 will have now m number of features. Previously, x1 has two features, but with this concept, we'll convert these two features, x1 and x2, will not be the now feature, and that will convert it to f1, f2, f3 up to fm. So f1 to fm will be the feature, and that is for single example. If you have another example, you have to calculate again. For example, x2 is another feature, that is given feature, but you have to convert f2 into sorry, if you can convert x2 into f1, f2 up to fm. So each and every example point will be converted into m number of features. So let us see the generalization in the next slide. So in generalized form, what does SVM do with kernels? Let us discuss about that. You will be given the set of data x and y for m number of example. We denote by x superscript 1, y superscript 1. X is actually number of features x will have. So x is actually a vector and y is a scalar quantity. It can be either 0 or 1 for our examples. So x1, y1 is a set of data, one set of data. So you'll give an n set of data and we will consider x1 as a landmark 1, x2 again as another landmark and so on. So total number of landmark will be total number of examples. So L1 up to Lm. Then for a certain x could be x1, x could be x2, x could be x3. For certain x, we'll have f1, f2 up to fm. So x is a vector that we have already discussed. X can be n number of features. It does not have to be m number of features. Rather, it can be say 2, 3 or 4 number of components. And that x vector compared with L1 vector will give you one scalar quantity f1. Similarly, when you compare that same x with another landmark, that will give you another component f2 and so on. So in our case, in SVM, we will have m number of features. So this m number of features will be for single x. So x in this case could be x1, but L1 will be equal to x1, L2 will be equal to x2. So this L1, 2, 3, 4 is actually different x's. So the formula will be like this. For certain xi, example I, it will be converted into fi. So xi example will be now fi. But you have to remember that the dimension of xi is not dimension of fi. Fi will have components of f1i, f2i up to fmi. You can see the number of elements in f is m actually, but number of elements in x we call it n. N is the number of features. So we are converting the n features examples into m features f's. So all f's are now m features. Same number of features. How to calculate f1, f2, f2, the same formula. When I say f1i, I mean ith example, then it is actually similarity of xi, that example point with L1. We already assume what is L1, what is L2, what is Lm. So L1 is if now fixed, L2 fixed, but xi could be any I. So I could be 1, I could be 2, I could be 3. So for certain example xi, we'll have xi similarity with li. You have to find out the formula. We have to apply the formula and find out f1. So this is a vector. This is a column matrix. So this is a vector, and that vector we call it fi, and that fi actually equivalent to xi. So there in this set of features, there will be one feature which is fii. The example is ith example, but there is element which is equivalent to same as I. So for example, you are considering third example, the superscript is 3. And this there is a term f33. There is a term f33. And that term is actually similarity of xi with li, because li is the landmark for that particular row, and xi is the example number. So in that particular element, which is fii, we can expect that that value is 1. So that is the maximum value, because the landmark and the example point are same point. So the closeness of these 2 points will indicate that that particular feature will be 1. Other examples will have less than 1, and the remotest feature will be 0 and close to 0, and the closer to the x1 the features will be close to 1. So now we'll define fi with additional bias term, which we'll call f0i, and we know fi we consider always as a 1. So this is the additional element that we have to add apart from m number of features. So total number of elements will be m plus 1, and that is our fi. So previously the given feature was xi, but for SVM we will convert that to number of features, and normally m is greater than n, so the feature number will increase. So how to actually find out the theta? The concept is similar to the previous discussion as we discussed for logistic regression. That hypothesis is given x, compute the feature f. One particular example, we have to calculate a particular f. X is a vector, f is a vector, but remember that x is only n number of elements, or with bias term it can be n plus 1, but f is a dimension of m plus 1 because there is an additional bias term and m number of features. So total number of feature is m plus 1. The training equation will be like this. That means the training means determining the theta. In every case, like linear regression, logistic regression, neural network, the training means actually determining the theta. So the determining of theta is followed from this cost function. The cost function we have already discussed, yi cost 1 of theta tfi, 1 minus yi cost 0 theta tfi, and remember the cost 1 is a linear equation up to certain limit then 0, and cos 0 is also a linear equation with 0 for the other part of the cost function. So this equation we have to minimize, and this is your regularization term. This regularization term plus the minimum error term, that multiplied by c multiplied by a plus b, that is your cost function, that has to be minimized for theta. The principle of minimization is same. That's why we are not discussing that one. What is the principle? Principle is you have to take the derivative of this equation, and since only one part will actually execute, so take the derivative of one part at a time. When y equal to 1, take this part. When y equal to 0, take this part. So once you get the derivative, then you just use that formula within a loop. Theta will be replaced by theta minus alpha into the derivative. So that part I'm not discussing repeatedly because that is applicable for each and every algorithm. So now let us discuss about some SVM packages. Those library, linear, liblinear, libSVM, library for linear kernel, library for SVM. So there are different types of library. So you can solve the parameter theta using a particular applicable library. So you need to specify the parameter c, and you have to choose kernel. Kernel that we have already discussed, the one particular kernel actually, that is Gaussian kernel. For example, if you don't apply any kernel, we call it linear kernel. No kernel means actually linear kernel. What is that? That is your predict y equal to 1 if theta tx is greater than 0. There is no conversion of the equation. The feature will remain as x. And this is normally applied when n is large and m is small. That means number of features in X is higher than number of examples. So that is the case where we will use linear kernel. That means that is applicable for your SVM. It's not actually, we call it SVM. In that case, we can apply the previous knowledge of logistic regression or etc. You can use SVM, but that kernel that you are using would be linear kernel. In case of Gaussian kernel, you will use that formula that we have discussed elaborately. And in that case, each and every Li should be equal to Xi. So this is applicable for when n is small and m is large, and need to choose sigma square. That is actually controlling the rate of or the how fast the convergence will appear. So these are the some notes about the software packages, and you don't have to write down the code, you just have to use the package. So how to calculate the similarity function in Gaussian your kernel. In Gaussian kernel, there will be two parameters, one is x1 and x2. X could be the given x and L could be the chosen landmark. So there are two vectors actually, and x1 we call it xi and x2 we call it li, and li is actually each and every case li is xj. Remember that for each x there will be one L. So Lj is equal to xj and Li xi is the first vector. So the formula is same as the previous one, and f is equal to exponential of minus absolute value of x1 minus x2 whole square divided by 2 sigma square. And the note is do perform feature scaling before using Gaussian kernel. This is similar to the previous discussion that if the range of x are different from one another, we have to bring the ranges in the equal limits, and that is done by feature scaling. We discussed about feature scaling before, so we'll follow that discussion in this SVM also. So other choice of SVM. Not all similarity functions, similarity XL make valid kernel. Need to satisfy technical condition called Mercer theorem to make sure SVM package optimization can run correctly and do not diverge. So that is another topic of discussion that we will not cover in this lecture. So there is a theory of choosing the kernel, and many off-shelf kernel available like polynomial kernel. Polynomial kernel is determined by this equation. If you want to find out the similarity between X and L, then you have to compute this particular equation. X transpose of L plus constant to the power a degree. It can be 2, it can be 3. And there are other kernel like string kernel, chi-square kernel, histogrammic intersection kernel, etc. So we are not covering all other kernels. So if you are expert in one kernel, if you know the theory for the other, you can easily apply that one. So this is the discussion for multi-class classification. You remember we discussed this topic for logistic regression, and this is similar to the logistic regression, but there are SVM package which already built in multi-class classification functionality. So instead of two class 0 and 1, the class could be 1, 2, 3 up to k. So you can use one of those built-in package. Otherwise, use one versus all method that we have used for logistic regression. So what is that? Train KSVM, want to distinguish y equal to I from the rest. So one is, say for example, will be considered as y equal to 1, and other will be converted to y equal to 0. And then that will be converted as y equal to 1 and other will be converted to y equal to 0. So in that manner, you solve different SVM, k number of SVM. That means output number is either 1 to, after from 1 to k. So you have to solve this classification problem for k number of SVMs. Every time you will get a set of theta. So theta for first example, for example, this is the y equal to 1 and other is y equal to 0. So you will get theta 1. Then that is equal to your y equal to 1 and other is y equal to 0. So the solution is theta 2. So for theta, y equal to 1, theta 1, y equal to 2, theta 2. Similarly, y equal to k, theta k. So for each and every y, you will get a set of theta. And which one you will choose? Pick class I with largest theta it of x. So theta it, calculate theta it. For example, if your given x, that an unknown x is known, then you apply each and every theta with this equation and you will get a value. And for different I, that means 1 to k, you will have k number of values. So take largest value and choose the class for that unknown. The unknown could be in that group, could be in that group, could be any of the groups closest to it. Even it is in not in within the group, if it is something like there, it will find out which one is the closest, whether it is closest to this class or this class or this class or that class. And the principle is you have to calculate this equation, theta I transpose of x, and find out the largest one, and that the I which gives the largest one will be the class for that unknown point. So let us now compare logistic regression versus SVM. In the both cases we call number of feature n and we call R x is a vector which has got the n plus 1 number of elements. N is the number of feature, 1 is for bias quantity. So x vector is n plus 1 degree. M is the number of training example. If n is large relative to m, that is, for example, n is 10,000, for example, m is only in the range of 1,000, then use logistic regression or SVM without a kernel. You can use logistic regression directly or SVM. SVM means actually the cost function with linear equation, and logistic regression means cost function with logarithmic your expression. So we call it without kernel means actually linear kernel. So this is actually a practical guideline for using either logistic or SVM. So which one you will choose, it depends on the relative value of m and n. If n is small, number of features is small, but m is intermediate. For example, n is from 1 to 1000, m is from 10 to 10,000, then use SVM with Gaussian kernel. But n is small, the previous case was m is large, m in the range of, say, for example, 50,000 plus. Then create and add more feature. Don't remain satisfied with this number of features. You add more features and then use logistic regression or SVM without a kernel. So these are the three guidelines that you can follow in your practical life. Neural network likely to work well for most of these settings, but may be slower to train. Neural network, since it has lot of connectivity and it can be lot of layer, the time of computation may be very high with respect to logistic regression and SVM. So with this, let us conclude this lecture, and with this lecture we have understood that the SVM has got greater ability to have a nonlinear decision boundary, and that is possible because we are converting the different given x into their kernel. And thank you very much.